So what I'm going to do is, I think most people here were probably at the retreat on Monday, but since this will be a tutorial for a wider audience, I'm going to quickly go through a few things that I talked about on Monday, just sort of background of decays and a little bit of the math behind it and some like highlighted features and benchmarks and such. But for anyone who wants to follow along the tutorial later particularly, or I very much encourage if you were at that talk on Monday to just ignore me for a few minutes and check out this link that's listed here and go to the examples repository, because that's what we'll be following through for most of this hour. So with that aside, so like I'll have this QR code out for a little bit, but if you just search MWI examples and my GitHub username, John Deuce, then you should be able to find it. Or if you search decays. Okay, so with that aside, please feel free to interrupt me at any point throughout this. We want this to be a nice interactive tutorial and hopefully some people can follow along. So we're going to talk about computing T2 distributions with decays. So this will be a bit of a tutorial and we'll highlight a couple new features. So let's get started. So this is a one-line overview, or a one-slide rather overview of what this software does. So, and I'm sure many people here will be familiar with this, of course, but so this is Myelin water imaging and Luminal water imaging. The backbone of it is multi-exponential T2 analysis. So much like what you've probably seen, bi or tri-exponential fitting in your undergrad lab courses or such, this is multi-exponential. And we essentially want to take a measured exponential looking signal, like this purple signal being animated here on this decays logo, and break it down into its constituent exponential components. So for example, this signal here is simulated and it's made up of two components. There's a small amount of signal that decays rather rapidly and a large amount of signal that decays more slowly. And so what decays will do is compute this T2 spectrum, which is to say each point along this curve corresponds to a certain decay rate. So further to the left means that component's decaying faster, and further to the right means it's decaying slower. And so decays has kind of correctly figured out that there's only a little bit of signal that's decaying rather fast, that's this red bump, and there's quite a bit more signal that's decaying rather slowly. So the total amount of signal in each part can roughly be thought of as like the area under these curves, and that's how we might talk about fractions of the T2 distribution later on. So how do we compute this? So to get into the math a little bit, it's a non-negative least squares minimization problem. So what we have is we have this measured signal B, and we're trying to compute a T2 distribution X such that X is strictly positive. That's because we don't want to have a negative amount of signal for a given component. They should all be positive. That's just a physical constraint. And we're minimizing this simple least squares problem, AX minus B, and we add some regularization to make the curve look a little bit, well, not to make it look smooth, because we know that there shouldn't be random peaks here and there. We should have a prior that the component should be zero unless it really helps the data fit. So that's sort of a physical constraint that we know in practice. There are roughly, several pools in a typical voxel. It's not like a continuous distribution. This can also be thought of like from a Bayesian sense, like a Gaussian prior on the T2 distribution elements, like centered around zeros, where the standard deviation is like 1 over mu, something like that. So the matrix A that we're projecting this signal onto is a matrix of exponential basis signals. So more accurately, they're computed with the extended phase graph algorithm to account for some flip angle inhomogeneity and things like this. But you can think of them as simple exponentials with these little wiggles that help match up with the data better. And again, that's physically motivated. And so this matrix it's one column. Each column has a different exponential or exponential looking EPG signal, and each one has a different T2. So shorter on the left, longer on the right, and we project this matrix B onto there by solving this problem, or this vector B. And again, B is our measured signal. The regularization parameter is chosen in one of a couple ways, which we might talk about later, but it's a little bit of an internal detail. And it just, again, promotes this sort of smoothing that we expect from physics. I think I'm already going to pause quickly because this is basically the only overview of the math behind the case for the rest of the talk. From here, we'll mostly just talk about how to use it and what the different parameters mean and such. So if anybody has any questions about the math, I am happy to answer that now. Otherwise, we will keep powering through to the rest of the talk. Okay, that's kind of what I thought. I think most people have seen this stuff before. So what do we use this for? So as I mentioned, Myelin water imaging is a favorite application of everybody here. So what you can compute with this is essentially that little red bump from the previous slide, the small amount of the T2 distribution on the left. We know from biology that, well, from experiments of the brain's biology, that the white matter in the brain has these quick decaying components due to the myelin, and those are nicely highlighted in the myelin water fraction map. So if we just sort of plot the fraction of the T2 distribution that's below a certain threshold, we get a nice map which highlights the white matter. And so this is a result from decays. And as I mentioned, there are B1 and homogeneity corrections built into decays. So this is also output by the decays. So this is a flip angle map. And as you can see, it's relatively smooth, as we might expect, which is quite interesting because everything is computed voxelwise completely independently. So that's a good little verification. And also, of course, you can plot T2. So here's a geometric mean T2 of the whole distribution. You'll notice there's two columns, and I think everybody here knows why, but this is because there's a previous version of this toolbox that was written in MATLAB, which I rewrote basically just to make it faster. And these compute almost the exact same things. If you look at the difference map, it's really close to 0 everywhere, and it's even magnified by a factor of 10 relative to here. There are small changes where essentially I made little algorithmic improvements. So if something was solved approximately, in some cases you could solve it analytically and it made things a bit faster, although it changes the results slightly. I think that's pretty clearly just an improvement. And there's other small things here and there, but again, they're of that nature. It's essentially the exact same algorithm. Another technique, which is newer, from a few years ago out of Piotr Kozlowski's group, is luminal water imaging. So you take the T2 distribution and you look at a different part of it, and you can highlight certain regions in the prostate. And it's very interesting because by looking at the luminal water of the prostate, you can actually differentiate. If you look at the LWF map here on the right side middle, you can differentiate healthy tissue from malignant tissue in the prostate. So that's a really cool application that's starting to become popular. And you can see, I think these highlighted regions are the malignant tissue. So it really nicely differentiates from the healthy tissue. And so here's a big old table that basically just says decays is fast. So this is, in case you're wondering if you should switch from the MATLAB version, I think you probably should, but I'm a little bit biased. But so the top 3 rows here are on personal laptops. So this one is like my 5 or 8-year-old ThinkPad running an i5. It takes like 7 minutes or so. I just tested this yesterday on an Apple M1 with 8 cores, and we can get that down to like 1:30. So there's 2 different data sets. I've basically ordered it by, these are personal laptops. These are more high-end computers. And on the more high-end computers, you can start to get really fast. So on this like state-of-the-art Threadripper, and this is what we'll have on the scanner for the Reconstructor computer with 32 cores, so 64 threads. This is a super powerful computer. We got it down to 15 seconds by compiling decays and a couple other tricks. But yeah, so this is definitely fast enough to run on a Reconstructor, and I think that's going to be probably my project this summer. And okay, so of course there's a paper from a couple of years ago if you're interested in more details, but so I think that's already enough of the background. I think I won't pause quite yet. I'll just give a brief overview of what we're going to be doing for the tutorial part of this, and then I'll stop for a little bit of questions there. So just in terms of using decays, so where we're going to go with this tutorial, it's supposed to be very simple for anybody who's never used Julia before. We just take regular multi-echo images as inputs, store in the usual row column slice echo, so 40 images. We support as many file types as we can, so MATLAB, Nifty, PAREC, and XMLREC. These last 2 are thanks to Christian Kames. He actually wrote the official Julia file reader for these file types, so thanks for that. And we just depend on that, and we load it like a normal file now. And then these parameters are passed as just flag value pairs, so just like like a command line sort of feel. So to give a quick highlight, I'll go through these parameters in a little bit, but so the MATLAB function looks something like this. We just download it and you just call it like a regular MATLAB function with a certain amount of threads. This one chooses automatically, certain parameters for characterizing the T2 distribution, output folder, these sort of usual things. Similarly, there's a command line interface, which looks very much like the MATLAB interface. There are a lot of arguments, and I encourage you to check the documentation to read about these, and we'll go through some of them later. But it's a very similar feel, but you can just run it from the command line instead of through MATLAB. And something we won't be covering today, but is pretty fun, I think, is the Python interface. So there's a Python package called Julia, which you can download, and it will let you call Julia functions directly. And the module that we provide, decaes.py, will automatically install decaes for you. The reason we're not going to cover it is because this is it interfaces with the Julia API, so it's a little bit lower level, so it doesn't do file reading and a bunch of other helper things for you. You just call the Julia functions directly. So decaes.t2map.se core is a Julia function that you're calling from Python. So we're just not going to cover that today, but definitely if you're interested, check this out. And okay, so that's the end of my starter slides. I will quickly pause for questions if there are any before starting the tutorial part while I get the tutorial a little bit set up. Okay, so the tutorial is again from this first slide. It's the MWI examples repository. So what am I at, 15 minutes? Okay. So when you get to this repository, the first thing you'll see is a bunch of files in a directory. So the key ones to note here are decaes.jl. So if you look at this one, it's just a little Julia helper function that will load decaes for you. It will install it if it's not installed, and then it will call the decaes interface. So we'll talk about that in a second. There's a MATLAB function, which I think is how most people use it. And this is similar. It handles installing of decaes for you and call it arguments. And there's lots of documentation in this function. And there's that Python module I was just talking about that similarly lets you call decaes through the Python interface. And some examples folder, and importantly, data folder. So there's some example datas in here. So we have some images. So this is a single slice of a 56 echo image, and here's 8 slices that we're going to use for some examples later. And these are some settings files, which I will go through what these mean in a bit, but they let you pack all the many settings of decaes into one file for convenience. And we have some image masks as well that correspond to those. So in terms of the actual tutorials, so we have a brief intro. There is links to the decaes documentation. So this is possibly a little bit of a source of confusion if you're not familiar with Julia. So this is just the examples repository. There's also this repository, which looks very similar, but is the official Julia package repository. So when you add decaes to your Julia installation, it downloads it from here. This is a different README with just a more brief introduction, link to the JuliaCon talk I gave last year, and info for citing. But there's not too much here really, other than like a little quick start. The walkthrough tutorials where you should really start. And if you click on the documentation, there's yet even more documentation. So this is more in depth. So this is the documentation for the Julia package. So this is every time you commit to the Julia package, it updates these docs. And so this will have some more mathy overview, some more installation instructions, some background and reference papers. And what we're more interested in from this side is the command line interface. So this details the command line interface, everything you hopefully need to know about it. There is lots of documentation about each parameter, and I encourage you, if you have trouble finding something or something doesn't work, to check here first, because there is probably the answer you need in here. Otherwise, of course, I'm always open for emails and this sort of thing. We'll probably come back here later to look at some details of the settings. looking for reference, but for now, we'll come back to this. This is the tutorial repository again. And so I think what we're going to do then is basically get started following this tutorial. So ignoring the quick start because this is going to be a long start. Okay, so installation. So first things first, let's do this optional thing where we're going to clone this repository so that way we can get all this code and data. So I'm just in this folder. It's not got much in it. I'm going to, why can't I see? There we go, code, copy here. So this is just the GitHub address. I'm going to git clone this repository. So this downloads everything. And so now we have a little MWI examples folder. So also I'm running this on Ubuntu. So anyone who's on Mac, it will probably look and feel a bit familiar. Windows, maybe not so much, but if you use the Windows subsystem for Linux, that should help you follow along. But otherwise, many of these steps are quite similar. This is just downloading something from GitHub, for example. So, okay, so now we have this folder installed, and here's what the directory looks like. So again, this is that same data with the images and masks I was talking about, these same files. So, okay, so we've got this whole thing cloned. Let's go back to where we were. So installation. So what it has in this folder is the things I was just talking about, these decaes helper scripts, and also an example shell script for running the examples, but we're going to go through those one by one. This part I just went through, so I cloned this from the command line. You can also just download the zip folder and extract it yourself. Okay, and now we're going to quickly cover downloading Julia. So in case anyone's never used Julia before, it is quite easy to install. So you just visit the downloads page and download the folder, and there's a precompiled binary for your system. So if you go to download Julia here, so this is just julialang.org/downloads. If you just Google download Julia, this will pop up, and you just want to get whatever the current stable release is. Here it's 1.713. For Windows, there's an installer. For Mac, there's a similar thing. And for Linux, you just download a folder and it goes on your system. But what I actually recommend is using this package called Julia Up. So you downloading it manually is completely fine. This is basically how I did it until several months ago. But Julia Up is now close to being the official way to install Julia. So I think that this is just an easier way to do things. And so I'll show you how this works. So on Windows, especially if you have access to the Windows Store, I believe that's like Windows 10 and 11, then this is, they call it production ready. So it's used in like serious companies and this sort of thing. The Linux and Mac is a little bit more pre-release versions, but I've had absolutely no problems with it. So I could personally recommend it at least. So Windows Store, you can access it here and download it. For Mac and Linux, there's this little command here that will download and run an install script. So just for anyone familiar, curl is just a Linux utility that can help you download files from the internet. This is the download script, and this means run it in the shell. So I'm going to copy this and run it here. And so I've already done this. So it'll say Julia Up's already installed in the system. For you, it will give you some prompts, and you should just hit enter, install it in the default locations is easiest. And then you might have to restart your shell because it modifies your path to put Julia on the path. But now if I say which Julia, so there's a Julia installed in this Julia Up folder. So it handled the installation for me. There's some niceties that you get, so it can tell you what versions you have installed. You can update to the newest Julia, all these sort of things. So it's really quite nice. So this is now definitely my recommended way of installing Julia rather than messing around manually with system paths and things. But again, once you run that, you might have to restart your shell because it does change paths. So that's the easiest way to do that. But okay, so now we have Julia installed. We are ready to go with the examples folder. So, okay, so here we are in the examples folder again. So I think what I'm going to do is I'm actually not even going to install decaes and Julia yet, because if you use the MATLAB interface, you will not have to do that yourself. So we're going to start with the MATLAB examples. So we're going to switch over to MATLAB here. So here I have the Myelin water examples folder. I'm going to add it to the MATLAB path and then go in here. Okay, so here we have the decaes.m file. So now we are ready to get started with using the MATLAB version. So where am I here? Just going back to the, so what step am I on? Okay, downloading Julia, we've done that. Installing decaes. Technically, we're doing this first one. So if you use either this script, decaes.m, or the Python module, decaes will be automatically installed for you. Okay, so this part we're not going to do because we won't need to. We can do that later when we do the command line interface. So, yes, okay, so updating decaes is something you'll have to do from time to time, but probably it's been stable for a while, so it's not too important, but it's just a regular Julia package. You just update the dependency in the Julia package manager, and I'll show you how to do this kind of thing when we get to the command line interface later. So, all right, so now we're getting to the examples. So I just want to point out in here that I believe I say it, I guess I say it somewhere above, but the command line interface and the MATLAB interface look very similar. So a lot of these examples we can almost copy paste into MATLAB, and that's basically what we'll be doing. So let's just switch over to MATLAB for a second and like get decaes up and running. So a good way to check just the status of your installation is to run decaes help, and this will call the decaes version and run the help from the command line. So yeah, pardon these weird identifiers. I think that's just MATLAB doesn't like Unicode characters, and Julia loves them and prints them all the time. So that's a way to deal with.
Jonathan, there's a question in the chat which I can just read out. Just to confirm, I think I missed it. Julia does not need to be installed if the MATLAB command line interface is used.
Julia has to be installed, but you don't have to install decaes yourself. It will do that for you.
Well, thank you.
So yeah, so you'll have to install it probably through Julia up is this package that I was recommending before is the easiest way. And then after you install Julia, the decaes will be installed itself when you run it from MATLAB. So that's actually what happened here. When I ran decaes help, it started installing decaes for you, but it did require that there's a Julia installation available. And it's printed the help like I asked it to. So this is a lot of help messages that you're welcome and encouraged to read when you're actually using decaes. But for now, we will just skip that and go through some of the documentation quickly of this function. So there's some MATLAB specific inputs here. So this is just some brief overview and some links to the documentation and the examples repository. So yeah, so this mimics the command line interface quite strictly. You can pass arguments as strings, numeric values, and arrays of values. And so there's some MATLAB specific arguments that are not present on the command line that we'll quickly touch on. So you can pass a path to your Julia installation. This defaults to just Julia, so that requires it being on your system path, which something like Julia up will handle for you. Or if you add it to your path yourself, the number of threads. So this will actually be chosen automatically now, but you can manually set it to something smaller if, for example, I might have to do that depending on how Zoom handles the decaes running while running the Zoom. And then the project folder, you almost never need to touch this. This is just, if you notice, it makes a little folder .decaes in the same folder as the file, and this is just to store like some Julia package information. So decaes is installed as a dependency, and these are all the decaes dependencies that are installed. This is nothing you have to know about to use decaes. This is just regular Julia stuff. It just makes its own little project environment, sort of like a what do you call them? Like a virtual environment in Python. It's a similar idea. And then, okay, so a fun one is the server. So I think I actually will do that now. So this is basically it starts a little Julia server in the background, just locally on your computer, so that each time you run decaes, it doesn't take so long. So like because Julia, there's like some startup time associated with it. If I run like decaes and just call help, I basically don't do anything. It still has to like start up Julia, load decaes, load the help, exit, right? So this took like 10 seconds, but there's a so it's still an experimental option, and there's like a more robust way to do it, but it's, I think, working enough to try. If it gets into a bad state, you just restart MATLAB, the process will be killed in the background. But this basically uses another Julia package called daemon mode to make a Julia daemon in the background. And so there'll be Julia running there. So this time it took 15 seconds, but the next time I call this, it will just like talk to the already active Julia. So that there's some Julia running in the background. Again, it'll be killed for you when you close MATLAB, but that way you save like a, I don't know, depending on if you have, especially if you have a slower laptop and you're doing like interactive stuff, this could save you a lot of time, but it's definitely not at all required. So I just wanted to mention it. And then we have the more in-depth examples and required parameters and such. So for this, I think I will quickly jump back to the tutorial to explain what parameters are required and what they mean. So to recap where we are up to this point, so we've installed Julia. We've not installed decaes manually, but we've just used decaes.m to install decaes. So we did that by just calling decaes with the help flag. And we covered the server flag, which lets you run a little server in the background just to make things a little bit snappier. So now we're going to get to actually running Myelin water imaging, in this case, on some example data. So we're going to go through the required parameters first, just so everyone knows what these parameters mean, and then we will run a couple examples. So there are some things that are required that are handled roughly for you. So the matrix size and the number of echoes. So these are just read off from the size of the image that you give. So the first 3 dimensions are the matrix size, and the last dimension is the number of echoes. You don't have to supply that yourself. The echo time, you definitely want to supply this. So this should be decaes assumes a uniform echo spacing for your multi-spin echo sequence, and you want to pass this in as a parameter, TE. Next is the number of T2 bins. So typically 40 is used, and you shouldn't have to change that, but it might be worth investigating depending on what you're looking at. And just note that, yeah, increasing or decreasing the spacing, so increasing the number of components or decreasing the spacing between components, for example, making your bounds a little bit tighter, will affect the regularization. So that's just the reason that it's often a good idea to keep it fixed. And just to go back to like the animation here to get something. So the number of components will be essentially the discretization of this distribution here. So basically how many components there are there, or that's what the NT2 is. So the higher that number is, the finer the resolution of this, but the trade-off is you have to regularize more. Again, that's done automatically, but still that's what's happening in the background. Okay, so then the T2 range. So this is the width of the T2 distribution. So what you want to do is start this at a number that is something around your echo time, because if you're trying to infer a T2 component that's much shorter than your first echo time, you're just not going to have enough information there. That component will have decayed so fast that there's essentially, there's not enough information in the data, and you'll just overfit to your data. So you don't want to make it too small. And on the other hand, you don't want to make it too big either. So something like the total length of your signal. So if you have like 32 echoes with a 10 millisecond spacing, like, you know, some small multiple of 320 milliseconds, 32 times 10 is a good idea. So like a second or maybe 2 seconds, because you also can't infer arbitrarily long components, because those start to look essentially like constant signals. They decay just so very slowly. They have a very small effect on the signal, and it's hard for it to figure it out. The most important thing is to choose one set of settings and stick with it. That's also a common theme, because that makes comparisons much more easy. So the small peak and the middle peak windows. So these are used in, for example, for Myelin water imaging. So we have the small pool window characterized as Myelin, and the intraextracellular water signal is characterized by the mean pool or middle pool window. And that's essentially, going back again to this graphic. So the SP-win lets you pick where this red peak should be, where you expect it to be, so the cutoff lines. And the MP-win lets you choose this, the green. So for Myelin water imaging, the typical thing you might do would be something like you start at the echo time, the TE, so to match your T2 range, and you cut it off at 25 milliseconds or sometimes 40 milliseconds. And the MP win would then start at the same value as the upper bound of your SP win. And your upper bounds might be 200 milliseconds if you're specifically looking at IE water, or it might be the whole range of the T2 distribution, the T2 range, maybe up to a second or two if you wanted to capture everything that's not the Myelin signal, for example. Similarly, in luminal water imaging, the MP win controls the luminal water window. So typically you would do, it's sort of the opposite of Myelin water imaging. This SP win would be up to 200 and the MP win would be from 200 to the rest of the distribution. Again, this is the upper bound of the T2 range parameter. And finally, the regularization method. So I won't go into this in too much detail, but there's lots of documentation to check out. So we have 3 methods. So there's 2 parameter-free methods that are new compared to the old version, new, I think. And then one method with 1 parameter that most people here are familiar with. So I guess I'll start with this one. This is what people know. So this is, you use the chi-squared goodness of fit method. So you basically, you solve it with no regularization, and then you choose the mu, the parameter, how much regularization to do by choosing, basically finding the mu such that regularizing it by mu amount corresponds to say 2% or 1% worse of a fit. So you trade off a little bit of fit imperfection for some regularization, and you choose that amount. That's the 1 parameter. These methods do that parameter free by the L-curve method and the generalized cross-validation method. These are sort of standard methods for choosing regularization parameters for linear systems. They're also, it's a really hard problem choosing regularization parameters, but these are pretty solid methods. So I think, again, general theme, pick one method and stick to it. Definitely don't compare results using different regularization methods. That would just add a variable for no reason. So pick one and stick to it. The default, actually, no, there is no default. This is recommended. We recommend the L-curve just because it's parameter free, but if you have other data that you process using the chi-squared method, that's fine too. Okay. So these are all the required parameters. So that's going to be enough to start running our examples. So these examples here are written for the command line interface, but I'm just going to show you how easy it is to translate it to the MATLAB interface. So what we're going to do, we're going to start running this first example. So I'm just going to copy this into MATLAB and hopefully it doesn't just start trying to run. No, okay. And by the way, I assume everybody can see the text on my screen. It's not too small. I'll make it a little bit bigger. I'm not sure how to make it bigger, but okay. Let me know if it's too small. We'll figure it out. But okay, so to set this up, we delete this Julia and replace it with decaes. We're calling the MATLAB decaes function. We can actually use this the same command line syntax. So threads equals auto, that's fine. So that's the MATLAB, and then we just get rid of this because this is for the Julia interface, and we are pretty much done. So we just wanted, so these are line breaks in MATLAB, this backslash is a line break in shell, and this should run. So what we're doing here is, so we're calling decaes with this, the MATLAB interface specific, this flag, so the threads equals auto. This is actually the default, so actually, maybe I'll just remove this just so that you can see you don't need it. The first argument is a path to the image that we want to process. So that is in the data folder, images, and actually maybe oops. Move this a little bit. So that's one of these images, this first one. And so these are the parameters we just mentioned. So, yes, there we go. We're actually going through this. So this is this, and then T2 map and T2 part are passed. These are not required, but they tell you what you want to do with the data. So this is, most of the time you want to pass both. So the T2 map means compute the T2 distribution, and T2 part means compute the parts of the distribution. So that's like the Myelin water fraction and the IU water fraction, for example, or the luminal water fraction. And then these are the flags that we just talked about. And then there's an output flag that allows you to specify where you want the results to be stored. So that's what we have here. So T2 map and T2 part. We pass in the parameters for the scan. We set 40 T2 distribution components. This is definitely a typo. All right, I gotta update this tutorial. So this should be, well, typo is strong. We recommend setting it equal to TE. Setting to 10 milliseconds is also fine. It just means you won't be estimating as many short components as you could be. Probably a good default is setting it to TE, the start of the T2 range the same as the TE. And then definitely you want the SP win to match the start of the T2 range. Otherwise you'll miss some of that data for no reason. And then this matches the MP win, which we cut off at 200. And we use the L curve method, and we store the output in this folder, output basic. Okay, and now we run it. So because I didn't use the server flag, it's starting by starting up Julia in the background, loading decaes, and then calling the entry point function. So that'll probably take like 10 seconds. And okay, now it's starting. Hopefully my Zoom doesn't start lagging. Please let me know if it does, because it is compute intensive. But okay, so now we started processing, and so this is just a single slice. So again, this is Julia has to compile things, and then, all right, and now it's done. So yeah, it took about 20 seconds to do that slice. And then let's try again with the server flag, just to see, at least the startup should be faster. Yeah, okay, so it started up a little bit quicker. So yeah, it's a bit snappier. And then it'll do the same thing, load the image, and it will write things into the output folder that we asked it to. So in the output basic, we now have some data. So I'm just gonna wait for this to finish quickly. So there's a log file. So this is useful mostly for me if people are asking questions, but if you come into problems, you can check this log file for, so it should be printing things like, yeah, near the bottom. So things like it will print the decaes settings that you used. So in this case, you can see, for example, what did we set? So we chose the L curve method, we set T2 range, we set echo time, we use multi-threading, things like this. And it also prints our T2 part settings. So these are the small pool window we used, the range which matches the other range, and the mid pool window. And so now we can look at some results. So there's a few files produced by this. So the first file is the T2 distribution. This just stores one 4D matrix called dist, which you can see here. So if I type whos, there's one 4D file. So it's the first 3 dimensions of the size of the input data. And then there's 40 T2 components. So, and then the next file is the T2 maps. So these are the things you're probably more interested in. So the first thing we could plot is alpha. So this is the B1 map. So if I look around here, so the values of this are, so there's like 150, around like 170, 180. So this is sort of what you expect for a flip angle map, and it looks rather smooth, which is nice. And oh, again, I should quickly point out, so in the command line interface documentation of the documentation, you can find information for these outputs. Sorry, rather they are in the API reference. So these are documenting the internal Julia functions, but you also can check this out to get more information for the settings, because these also have lots of documentation too. So, okay, so here, this is what's outputted by T2 maps. So we just looked at alpha. So these are the optimized refocusing flip angles. So this is what's estimated by decaes to get the B1 map. What else can we look at? So GGM is a nice one. So this is the geometric mean of the distribution. Let's try that one quickly, GGM. So, okay, the scaling is a little bit odd, but you can see that it's higher in like these regions here, and then, yeah, so these are like 50 milliseconds. This gets up closer to a second being water. So let's maybe make this color bar a little bit. There you go. So that looks more like something you might imagine. So this is the T2 distribution. And then, so then there's some other information in here that you can check out. in the docs, and then the final file is the T2 parts file. So okay, I'm just going to clear everything else so that you can tell what's from what file. T2 parts file. So we can see this down here. So the SFR parameter, that's the small pool fraction. So in this case, that's the mile water fraction. So let's plot the SFR. And so here, let's make that color bar a little bit better. Yeah, so here's like the mile water fraction for this image. So we have, where's my data tab? So we can look here, we get some values like we might expect. So there's, between 10% and 15% kind of thing. It nicely highlights the white matter. And it's very small, like in gray matter regions, are forced to zero even thanks to our Gaussian prior, or our regularization rather. Okay, so this is the most basic example that we have. It's just a single slice, and you process that using the MATLAB interface. I think we can get on to a couple more features. Again, please feel free to interrupt if you have questions, but I think I was just going to get to some other features quickly next, but all those are in the documentation as well, so I'm happy to answer specific questions while I'm here. So some things that people will be interested in if you're actually using decaes would be this one, so passing masks. So this basically makes things faster is essentially the point. It just skips all voxels outside of the mask just to save computation time. Otherwise, it's the same. So if we look back at our example from previously, all we've changed here, if we've added this flag mask going to this file. And actually, I think we use a different regularization method, but that doesn't matter too much. We'll just leave that for now. And so we add this flag and make sure it's for the right image. And we'll put this in a different folder, output mask, and run that. And okay, so that ran really fast. So now we have the mask folder. So clear everything. We'll load the T2 parts from there, and we'll plot the mile water fraction again. And so you can see it's the exact same thing. I'll even compare them quickly. Okay, well, I should have opened a new figure, but I think you get the idea. The other one was the exact same thing, but just with the brain region masked out so that there's none of this stuff from the outside. And of course, you can pass any mask you like, and it's particularly useful if you're looking at certain ROIs. So it'll make it run much faster if you're looking at only some small region of the white matter, for example. So that's just a handy feature. The other one is processing multiple files at once. So to run it in sort of like a batch mode. So here we can run this running with 2 images, and then we'll pass both the masks for the images as well. So all you have to make sure is that if you pass multiple files and you want masks too, you have to pass 1 mask for each file, even if it's the same image or the co-register images with the same mask. You still need 1 file per thing, 1 mask file per input file. So let's try running this example. So we'll run this guy again, and what we're going to do is just add a second input. So this is the second file. So this is basically the same image, but it's just 8 slices of it, so it'll take a little bit longer. So let's add a break in here. All right, so we got 2 image files, and we'll add the second masks file as well. Yes. And what do I call them? Output multiple. And hopefully I didn't make any typos. Number of mask files. Oh, okay, that's because I put the mask flags twice. So 1 flag, 2 files. Okay, there we go. So the first one ran super quickly. It just flew by. I don't even know where that ended, in like a second or so. And the second one took about 3 seconds. So now those are in this folder. So now you see it stores the results for all the files with the image name prepended, and then the .t2dist will be the distribution for this first file, the t2dist distribution for the second file. And so if I load, say, the T2 parts for this 8 slice image, I can now plot the malware fraction, let's say, of the first slice of this image. So that's that one. So I can figure plot the second slice, or plot all the slices one at a time. So now we got, there we go. So this is the first, second, third, fourth, fifth, sixth, seventh, and eighth slices. Yeah. So this is just stored as a 3D matrix in the same size as the input. What else we got? Oh, settings files. Okay, I don't want to forget about those. So those are very convenient, and they avoid having to mess around with passing all these parameters in the command line. As you've seen, I've already messed up typing it once. So this is a good advertisement for settings files. So in the data folder here, we have some settings files. So these are the same 3 examples I just ran, but just with all the examples written out at once. So even the same typos. So this example 1.text, so that's the very first thing I ran. You have it here, and then you just put every parameter one by one with 1 parameter per line, including if it takes 2 arguments, like T2 range, 1 on each line. And then what you do to run it is you just go to decaes, and then you say at the settings file name. So I think this is, MATLAB should auto-complete this for me, maybe. Data, nope, not, okay. Well, data example 1.text, and that will run that. And you can actually chain arguments together. So I can say first, say I want to run on the server, then I have this default settings file, and let's see what's something I want to change in here. Let's say the MP win. I don't want to only look at that region. I want to look at the whole, what's my T2 range up to 2 seconds, the whole range. So this will overwrite the settings file. So it'll do everything like this, except for it will do the MP win with that parameters because it's the last input. So that's done. And if you just want to double check here, the MP win is indeed set to what we asked it to be, 25 to 2 seconds instead of this. And you can actually even do this with multiple settings files. So if I had, say, a settings file that's like my default settings, and then maybe like, my settings for this study or something, like some like small modifications, my modified settings for this study, something like this. You can chain them together, and whatever's added last will be used last. Something that probably you don't need to use too much, but I use often when I'm testing things, you can add the dry flag, and that will basically do a test run, and it will just do everything without saving. Oh, because that's not a real file. My default settings. This one, dry. So this will run everything through, and it just won't save anything. So that's good for just testing to see if your, I don't know, computer can handle those parameters or something like that. Probably you don't need to use it, but it's a good one. It's available. What else do we have? So there's some example scripts as well. So let's go back up to these at the start. So these basically just have the examples that I just went through. So maybe we open them in MATLAB, that's better. So this is the same examples file. So here, this is running this first example I just went through. These settings, same one here, and same one here. And then we also have a shell script, which does the exact same thing, but from the command line and using these settings files. So I think while I still have a couple minutes, I'm quickly going to jump over to the terminal and just show how to use decaes from the terminal. It's quite simple. The only thing we have to do is first install decaes ourselves, since we're just calling Julia. So here I've started Julia. As you can see, this is 1.7.3. It's the latest version. If I type this character, that enters into the package manager mode. So I type like this, the bracket, and I can say status. And these are my current Julia environment. It's totally blank. There's nothing there. And now I'm just going to add decaes to it. So this will download decaes from the decaes repository and install it. So now it's ready to go. For example, this is just regular Julia using decaes. It will load decaes, and then we'll have some functions available. So I can go help main. And so this is the command line interface for decaes. So, and then actually using it is basically just like regular Julia. So here, I'll copy this example here. So this is from the shell script. So Julia -threads equals auto. So this is telling Julia that you want to run it with threads. DECAES.jl is this helper script right here. So again, I didn't have to go and install decaes manually myself. Actually, if I use this script that we provide, it will do that thing for me. pkg.add is the exact same thing as what I did here, add decaes. So Julia threads equals auto tells you to run it multi-threaded. Use this script to call the Julia interface and then run that first example. And this will just do the exact same thing the MATLAB interface just did, running that for that single slice. And the syntax is almost the exact same. You just put this little separator in between. So these are Julia flags and these are decaes flags. So this is just regular Julia code. It's calling this Julia script. There's a separator and then the example or the flags for the rest of the processing. And so this is running, and then it will save the outputs in the same file, probably overwriting some examples. Oh no, it stores it in this folder, output example 1. And you can see these are all ready to go here, just like we saw before. So this is the water fraction produced there. Okay, so I think this is close to the end of the walkthrough tutorial. I want to leave a few minutes for questions since I went a little bit fast through certain things, but the main resources to keep in mind are, of course, the walkthrough tutorial, the MWI examples repository. So this has everything and more that I've gone through, and the decaes documentation itself. So there's, like, if you search decaes, it'll go to the Julia package here. And if you click on the docs, you'll enter these docs, and these have lots more information and specifics. So it has everything you need for the command line interface, including, so there's some new features. So let's actually quickly go to here. This one's new, so B1 map, so that flip angle map alpha, so this one, you can pass it in yourself if you have an estimate from somewhere else. Oops, I did not load it. So yeah, so the flip angle map, if you have an estimate of this from somewhere else, you can pass that in. Just as a regular file, so a parec file, a nifty file, a MATLAB file, whatever, just a 3D array of the flip angles. There's some other parameters for extra things you might want to save. For example, the residual norm, so that's how well the solution fit. The regularization parameter, things like that. Oh, there's bet. So if you don't have a mask, but you want to call bet to produce one for you, decaes will support that. So let's try running that. So this should make so the first thing it did was it called bet to make a flag or a mask real quick, and then used that mask and then ran decaes afterwards. So it's a good way to make a quick and dirty mask and you can pass bet arguments to it. And an experimental thing, but is working quite well for us, is compiling decaes. So this will get rid of a lot of the overhead. So if you use it from the command line, you can compile it once and then get rid of that overhead. So for example, the reason we use the server flag on the MATLAB interface to get rid of the overhead when calling it from MATLAB. But if you compile it, that's no longer an issue. So that's another option. But yeah, I think I will cut it off there. Thank you everyone for listening, and I will take as many questions as time permits. And yeah, just keep in mind, there's lots more in this documentation. I tried to make this as thorough as possible. Thank you.
Awesome. Thank you so much for that super comprehensive overview. That was really fantastic. And the video is going to be a great resource for people in our group currently, new people coming in, and then anybody else out there who wants to kind of use this, right? So excellent. Thank you. Any questions for Jonathan? There's a comment chat.
I have one.
Sure.
There are also some studies where they do, like, low number echoes, acquisitions, and then do a single exponential fit, like T2, for example, in cartilage, where there's like 7 to 12 echoes or so. Do you think decaes would be useful for that as well?
Yeah, so right now it doesn't fit the T2 values. So the T2 values are fixed. You set the range and the number of components, and it logarithmically spaces them and just fits for the coefficient. But yeah, I think we've talked about this before. We could definitely add like a mono-exponential fit kind of thing to this, or the current thing decaes would be useful for would be it's not a mono-exponential fit, but you fit the whole distribution and you look at something like the GGM. So that's like a more, I guess in some sense, it's a more robust T2 estimate because you account for the flip angle and B1 homogeneities, things like that. So short answer, yes, I think it is useful for that, but it's slightly different than a mono-exponential fit.
Yeah, of course. Okay. I think we should try that. Thanks.